If you've ever taken a multivariable calculus class, you know this integral is a classic rite of passage because e to the negative x squared has no antiderivative. We were taught one of the ways to solve this is to square the entire integral and use a polar coordinates trick. And honestly, it's a great proof, but I always felt like converting a simple looking problem into a double integral is a bit of an overkill. But in this video, you and I are going to explore a way to bypass the double integrals and use an identity from 1655, which is Walli's product. First, let's look at the multivariable proof so we know how it unfolds. We square the integral and write the second term using dummy variable y, and by Fabini's theorem, we can combine and write them as a double integral. And now we perform a change in coordinate system from Cartesian to polar. dx dy equals r dr d theta can be proved by using simple geometry, and as a clue, the r d theta is the arc length and the dr is the element's radial length. And it makes sense how covering the whole plane in Cartesian system in polar form is basically having an infinite radius and covering the entire 360 degrees or 2 pi radians. Sit back and relax. Now we just finished the hard part and it's time to do the math on autopilot. After some simplification, we arrive at square root of pi. Simple. Now let's talk about the real deal. In the first step, we identify that Euler's constant E can be written in its limit definition. This is seriously a high IQ move. And then we bring the limit out of the integral. But we have to be careful though, as it requires dominated convergence theorem to be valid, and fortunately it is. And this is the only part where it requires some rigor, but for now, let's continue. You might argue, can we really replace the infinities with the square root of n? I mean, why square root of n? We could have used different rates for positive and negative infinities. Actually, you can, and since the integral converges, we have every right to choose whatever we want, except when we choose square root of n, we can work out the integral with ease, and you'll see what I'm talking about. And we get this. And where do we go from here? If you ever came across Walli's formula and how it relates to integral of sines and cosines from 0 to pi over 2, you can directly solve it from here. But where's the fun? Let's derive the reduction formula and manipulate the expression a bit. We can definitely notice a pattern here. If it still doesn't make sense, you can take a value for n and use the reduction formula and realize how we always end up with 2/3 and that I1 at the end. Now, save this I sub to n plus 1. Remember that we would substitute this in our limit argument later. Now, before we proceed, we have to recall what Walli's product for pi looks like, because we are going to try manipulating our infinite product to match this. From here, I want you to observe carefully how the algebra plays out, and you can pause the video in places you don't fully understand to get a better look. Isn't that beautiful? As a fun fact, I had almost come up with this method myself, but before me 3 centuries ago, Laplace and Euler have already found this method. But I was fascinated because I haven't seen anyone prove it this way, so I had to share it. If this video satisfied your curiosity, then I'm sure you'll enjoy this video too. And don't forget to ask your doubts in the comments.